Welcome. Today we're going to talk about U-substitution, which is the second really big idea in this chapter. First was the fundamental theorem, next is U-substitution. We'll talk about the idea, what it means, and do lots of examples. We'll work through them slowly so that they make some sense. So U-substitution, what it really is the chain rule, but going backwards. So if you recall the chain rule, f of g of x, the derivative, you take the derivative of f, add g of x, times the derivative of g. What we're going to do here is notice that inside the integral, when we have an f of g of x, well, imagine that's a prime there, of g of x times the g prime, that's the derivative. I'm going to get rid of that because I'm not actually doing the antiderivative yet, but I get rid of all of the inside by doing a u substitution. I say u is this thing inside. As long as this derivative is here, we don't need that anymore. What is it doing? It's saying, let's do the chain rule in parts. Let's do the antiderivative of the chain rule in parts. We're saying, I've got a chain rule going on. I'm going to do the inside piece, get rid of it, so I can look at the outside piece. Now that may not make a lot of sense right now. Let's do an example. Hopefully it'll make more sense. So, here's my example. I want to take the antiderivative of 2x e to the x squared. Hopefully you can see there's an inside function. E to the something. This is e to the something. And I know there's rules for e to the x, but not e to the x squared. So looking at this, I say, what could be my u? U is the inside function. So right now I'm going to say u is x squared. And the goal is to remove all of it from the integral to make the rest of the integral easy. We don't forget it, we'll bring it back when it's done, and we can work on it. Now, if you call over here, I'm going to end up with a du. This is where the dx, du makes a big, big, big difference. It was a dx, all of this is du. A way of doing it, you could say, formally, du dx is the derivative of this. Or another way of saying that is du is the derivative of this, 2x times dx. It's not really multiplication, but essentially that's what I'm doing. So du is all of that. If I have all of that, I call it du. Why? Because that's how it's going to work. That's the derivative of the u function. There's my du. It's built into this one. There's no work involved. It's just right there. It has to be multiplied on. It can't be added. It can't be divided. It can't be piecemeal, part of it here, part of it there. It has to all be multiplied as a factor in the whole thing. But then if it's there, which it is here, we have e to the u du. Because that's our u, that's our du, e to the u du. Now the reason this is nice, look at that. We're saying what is the antiderivative of e to the u with u being our variable? That's just a straight antiderivative. So the answer is e to the u, but of course this is an indefinite integral, so it's plus c. And now, we're not actually done. We did do the integral. But the original problem was in terms of x, and we should answer it in terms of x. There's a u in here, and u was something we created, not the problem. So we have to figure out what to do with that. But we know u is x squared. So we do that. This is e to the x squared plus c. And there's our answer. Now look at this. There's two things multiplied together. What happened to this one? Why is it two things turned into one? Because if you took the derivative of this, e to the stuff, you get e to the stuff times the derivative of the stuff. That's the times derivative of stuff right here. We're just absorbing it in a two-step process so you don't have to remember it all at once. Here's another one. Hopefully you can see sort of what to do. Give it a go, and we'll look at it in a second. Okay, so the first thing to do is to recognize it is a chain rule, something going on inside. We've got something raised to the 10th power. That's a really good choice for our u. It doesn't always work that way, but usually it's an inside thing. What's the inside thing, or the thing in the weird spot? Now, in order to do that, we need to have a du. That's our u. Du is the derivative of that, which is 4x cubed. But it's 4x cubed dx. The dx is part of the du. It's absorbed into it. Do we have 4x cubed dx multiplied on? And the answer is no, we don't. Up here we did, it was perfect. Here, what are we missing? We're missing the 4. Can I just put a 4 in there? And the answer would be no. But is there something I can do? I could put a 4 here, and then divide by 4. I can always do that, right? That will give me the 4 I need. It'll just put another one in that I don't need. So let me rewrite this. I've got that 1/4 that I don't need. I've got 4x cubed. I've got x to the 4th plus 7 to the 10th dx. Is that right? That's all 4 pieces. There's the 1 piece, the 2nd piece, the 3rd piece, and the 4th piece. Now I'm going to need another color because I just wrote that in blue. But this and this are my du. This is u. So, when I have this form, remember if you've got f of u times du, that's all you need. You just rewrite it that way. So this is going to be, the 1/4 has not gone away, it's the extra along for the ride, but that's all du. So I have u to the 10th du. Now that 1/4 may throw you off, but remember you can always pull a number out of an integral. So that 1/4 will come out. And actually, normally I would just do the integral now, but let's do it at one more step, just because. Anti-differentiate u to the 10th. Anti-differentiating means we add 1 to the power, so we get 1/4. Then that's 1/11th, u to the 11th, and it's indefinite, so it's plus c. So we end up with 1/44, something to the 11th plus c. And what is that something? It's u, but we don't use u because u is not part of the original problem. We use what u is. It's x to the 4th plus 7. And I'm going to rewrite that 44 because that looks a little weird. Hopefully that makes some sense. Let's try another. This one has 2 things going on that are slightly more interesting. One of them is it's a definite integral. So what do you do with those limits? We'll talk about it. The other is there's no inside. There is a natural piece to worry about. I'll give you a second to think about it. Try to find the u. Hopefully you can tell. U is going to be the thing, 2 things about it. One, it's hard to use, and the second is its derivative, maybe with a constant missing, is around. U is the thing on the bottom. Why is that? Because the derivative of that, 2x plus 2 dx, there's an x plus 1 multiplied on. So let me rewrite that. That's 2 times x plus 1 dx. We have this piece, we have that piece. They're both in there. We need a 2, and then we're good to go. So just like we had before, we'll put a 2 in there and a half in there. Let me write that. 1 to 7, 2, x plus 1 over the 2 on the bottom. They would cancel. Of course, that would defeat what we just did, but that's the goal. Okay, so that takes care of that. Let's do the U-substitution. Here is, that's du. So this is equal to 1 over 2u du. Now there's a couple things. That 2 there, I'm going to have to deal with. The second thing is, what do I do with these? There are 2 options. One is to ignore them until the end. Once you've done it, bring it all back. And that's what I'm going to do here. I'm going to pretend they don't exist and then bring them back at the end. The other option is to convert them. And I'm going to do that in the second example. Both work perfectly well. Some are better, some is better than the other way. But right now I'm going to ignore. I get the 1/2 pulled out. This integral, hopefully you remember, is the natural log. It's the natural log, technically, of the absolute value. It's not plus c because we aren't really going to be using, it is a definite integral, so you don't need to do that. But here we go. It's 1/2 ln, that was the u, but what u is x squared plus 2x plus 3. And that goes from 1 to 7. That's it. This 1, this 7, those are x endpoints. They are not u endpoints. So when we switched over to a u integral, they disappeared temporarily. When I come back to x's, they reappear. Those are x's, so I put them in. I get 1/2 ln of, plug the 7 in, 49, 50, 51, 52, 66, minus half ln of 4. That can simplify. We can divide. I don't really want to do it right now. That's the answer. Let's do one more. And here it is. Okay, what do we do? Well, hopefully you can see. There's something inside. That's going to be our u. If u is pi x, what's du? The derivative of that, pi times dx. Well, the dx is there. There's no pi. So again, we have to create it. It's pi over pi cosine of pi x dx. The dx and the pi, there's our du. Let's go back to black. This is going to be 1 over pi cosine of u du. Now I said I was going to switch the limits this time. So these are going to be u limits. If u is pi x and x is minus 2, plug minus 2 in there, we get u is minus 2 pi. The top one, if x is 3, that becomes 3 pi. Now notice, this is a definite integral. It no longer has anything to do with x. X is forgotten. It's all been absorbed and changed into strictly a u. So now it's no longer something we have to worry about. I'll pull the 1 over pi out. And then I have to anti-differentiate the cosine of u. What function, in terms of u, produces a derivative that's the cosine? And the answer is the sine of u. Went from minus 2 pi to positive 3 pi. So now we plug values in. Notice we never had to go back to x's. On the top way, once you did this, we went back to x's to keep the x numbers. But if we're going to substitute in the new u's, we don't have to do that. The x's are gone. 1 over pi sine of 3 pi minus the sine of minus 2 pi. And if you remember your trigonometry, you know that that's 0, that's 0. This is 0. Try them out. Until next time, this is Dr. Chen.